And it's actually on a topic which has been fascinating me for the last 25 years. What is the difference between data and information? And how is data and information changing over time? I was visiting a seminar on the teaching of computer science in Newcastle, organized by Brian Randall about 25 years ago, or more than that, 30 years ago, on a talk on data and reality. And this talk was excellent, but it raised more questions than it gave answers. And so this was actually the starting point for this work, which has a clear purpose. And because I think when you design a system or you do some work or you build something, the first thing is you should get clear what is the purpose for doing it. And I think this is very important, sometimes overlooked. People sometimes start with requirements and I think it's too late. We should start about purpose first. And the purpose is here to get clear semantics about the terms data and information, to provide a framework to show how data and information changes over time, and to look at the investigate the communication among humans and machines, and about machines to machines, and to look at the difference between archival data and real-time data. And at the final section, I will give you a few slides to show how the understanding of the DAT model can help in the design of real-time computer systems. So that's as a start. Now, when we look at communication in the dictionary, it says a communication is a process by which information is exchanged between individuals by symbols. A common system of symbols. So I don't like the word science here, or behavior. Or the functions of pheromone in insect communication. I will cover both aspects of this definition. And in human communication, the basic means for getting information from one mind to another mind is by natural language. Human communication is basically using natural languages that are exchanged between speakers and listeners who understand the language. And the meaning of a word in natural language, which I call a data item, the meaning of a word is a data item, is a concept in the mind. And what is a concept? A concept is, there are many definitions around, but the one I like best is a unit of thought. A unit of thinking is a concept. And if I have a word, let's say a house, the concept is what I have stored in my mind by the house. And a word has a denotation and a connotation. The denotation is a concept that is shared in the language community, and the connotation is my private view of the word. So this is some difference between what is shared and what is private. And to give you a short introduction, in the DAT model, information is the sense, the idea communicated by a basic natural language sentence. It is composed of meaningful words. I mean, if I say, this person is, I don't know, 25 centimeters high, this is a sentence, and the words are understood, and this make a proposition, as I call it, and the proposition makes sense, and the sense, so to speak, is the meaning which I assign to such a sentence. So the first insight, we capture a word has meaning, but the proposition is needed to make sense, to give you information. Now the question now is, how do words get their meaning? How do we assign meaning to words? And that's the issue which is in cognitive science and in philosophy, the symbol grounding problem. How do I ground symbols? How do I know what the word means? And there's a theory of embodied cognition, which has been started 25 years ago, that says words get their meaning, that they say their grounding in reality by identifying the word with bodily sensations. For example, if you take a baby, which is a pacifier in the mouth, And if you say, this is a pacifier, the baby will associate the sound of the word pacifier with the physical impressions it has by sucking the pacifier. In the same way, I can say, this is a tree, show it to a tree, and then the person will acquire the meaning of the word tree by associating the word with the associations. And of course, this is the basic concept established that way. Now that I have some basic language established, I can build up bootstrapping, further concept by using these basic concepts and get more and more abstract and complicated concepts. And this is the way we assign meanings to words. And we see this is very important when we talk about information and computer systems, because computer systems don't have this facility to acquire meaning by bodily sensations. Now, in the course of your life, you build up a knowledge base in your mind. And I call this knowledge base the conceptual landscape. That means you start out with these very basic concepts, you get more sensations, you get more complex, more abstract concepts, and all of this, the sum of all of these concepts are called the conceptual landscape, which is built up part by nurture and also part by nature. That some of the mechanisms in the conceptual landscape are actually innate to our human genome. And one idea which is important, the one is that this conceptual landscape is never fixed. It's always in flux. It changes as you live your life. You get more concepts. You see, the core of this conceptual landscape is normally rigid. And the problem is, the older you get, the more rigid it gets, the more difficult it gets out of this course. And Piaget has coined the term assimilation and accommodation. That if you see, or if I see, an external situation which doesn't fit in my conceptual landscape, there are two ways to live with this. Either to change my conceptual landscape, and this would be accommodation, or to assimilate it, to say what I see is not really that important. I can build it into my conceptual landscape without changing it. It is called assimilation. And if you get older and older, the accommodation gets more and more difficult because you think you have a fixed conceptual landscape and that's it. But the point is, despite all of that, the conceptual landscape is dynamic, and the subject knowledge base in the mind of a human is thus changing, and it is changing the meaning of words. And that time comes in. Because as time goes, the meaning of a word can change. Now, I've given you already two concepts, and I will go in the further part of the lecture, go into some other terms. I'm going through these definitions very quickly. You can look at them. We could discuss about these definitions, every one of them, for quite a while. But I call an entity is either a physical thing, like a table or a person, or a product of the human mind, which I call a construct. And so when I say entity, I mean either a physical thing or a construct. Now, what is a system? A system, to me, is a collection of related entities, which are normally called subsystems, that interact to provide a service to the environment. And normally you can think of the system as being encapsulated by a skin around the system, and the skin has interfaces. And the interfaces allow the system to interact with the environment. And in the interfaces, there are sensors and actuators. And depending on the sensing and actuating capability of the system, determines what you can interact with in the environment. If you are a bat, you can do different things than if you are an ant or something, because they have a different sensors and they have a different world model. So it's basically the sensors and actuators that determine your view of the world. Okay? It's a property is a characteristic or a feature of a thing or of a construct. So basically, if I take a stone, the property of a stone is the weight of a stone. And the value is a refinement of a property. I mean, if the stone is 50 kilograms, then the value refines the property weight. Very important in our language is the concept of a category. A category is a construct. It doesn't exist as such. It's a construct of the human mind that denotes a set of things or constructs, so it's recursive, that share identified properties. For example, if I say a house, I mean all the things which look like a house, okay? And then one of interesting constructs is time. And the time is a construct that can be depicted by a line that proceeds from the past to the future and is marked by the ticks of a clock. And I will use the following model of time in the DRT model. We assume that we have a clock, and let's assume for the moment this is a GPS clock, which ticks in 100 nanoseconds intervals, which is the granule of the clock. And I call a process which happens between two ticks an event, and the process which is longer than two ticks is a state, or a process sometimes, as I call it, which has a duration. That means if I have an event, I can assign a timestamp to the event. That means the tick number at the end of the event. And if I have a process or a state, I need two timestamps to denote the duration of the event, of the state. And this is the start and the termination timestamp. Now, let us for the moment forget about digitalization errors. That's an issue which is important, particularly when you talk about simultaneity. And if you're interested in it, I've written a book on real-time systems, and there's a full chapter about this issue, so you can go into it and look at it. But we can think that these kind of digitalization errors are errors of the second order, which, as a physicist, we are going to neglect for the moment. We stay with the main line. Now, I will use the term happening as an umbrella term if I don't want to say if this is an event or a state. So it's just something which has either one timestamp if it's an event or two timestamps if it's a state. So in our definition of communication and information, a symbol played a very important role. And what is a symbol? A symbol is a construct. A construct is a product of the human mind that has two parts, a signifier and a signified. The signifier gives us the physical appearance of the symbol in the physical world. It's a thing in a sense, the signifier. And the signified is what the symbol stands for, whatever the system stands for. So there always this signifier, signified, and this is very important. The signifier is sometimes called the name of the symbol, but that's not really the issue here. So a word is a signifier that has signified the concept behind the word. And this brings back the idea before. And we, in the DRT model, we distinguish between four different signifiers. Either a word in a natural language, and I already talked about words, the signified is a concept. A proper name, that means if I say Martin, I mean this particular person over there, so it identifies a thing or a construct in physical time-space. A literal is probably the more complicated issue. A literal is a signifier that has a special form that somehow denotes the signified. And a good example of a literal is a number. If we have the numbers from 0 to 9, we know by our cultural experience that it's an abstraction of the entities in a set. If I say 0, it's an empty set. If I say 9, it's 9 elements in the set. I'll go to the literal a little bit more because this is an important concept in our model. And finally, a token name. A token name denotes a placeholder in the abstract world of token, the token system. It isn't grounded. The token name is not grounded, and that's the difference between a word and the token name. If I say X is 5, I don't know what 5 means, because X isn't grounded. But if I say the age is 5 years, then I know that 5 means number of years of a particular person. Okay? Let's go a little bit in literals. a literal, the Gestalt of the literal, the English word Gestalt is also the German word Gestalt, means that the Gestalt denotes the signified. So if I have a sequence of digits, okay, in the decimal base, I see at the right side, you see I have 5 entities, 5 apples on the table, on the dish. I could use different numbering system. I could use decimal system, that would be 5, a Roman system, it would be a V. In binary, it would be 1, 0, 1, 3 bits, and in base 4, it would be 1, 1. So what a number really means depends on the context. We have to agree on the context to know what 5 means. The same for 3. 3 we can decode in very different numbering systems. And it always depends on the context to decide what 1, 1 means. And we have to agree on the context before we can know what is the meaning of a literal. A literal gets its meanings out of context. And this brings us to the issue of context. And in the DAT model, we distinguish between 2 types of context. Outer context, that's the context in the community that interacts, language, culture, sociology, all of this is part of our outer context, time, weather, climate, and so on. It's the prevailing physical, cultural, and social environment. That's the outer constant. And then we have an inner context, and that's in our head. And the inner context of a word consists of those parts of the conceptual landscape in the brain of a conscious human that are related to the concept denoted by the word. Okay? And of course, there are many interactions, many connections between words, between concepts in the mind, some of them known and some of them unknown. We don't know all the interactions between the concepts in our mind. There are many tacit interconnections. That's an issue which is, I think, very problematic, as we will see later. The question is, we talked about consciousness. And so this brings us a bit into cognitive science. And as I said, I had the time during the pandemic to look into different areas which are way outside the area of computer science. But I think you need to go into these areas. And I ran into the theory of neuronal group selection by Edelman and Tononi. And Edelman is an interesting fellow because he got the Nobel Prize for finding out the human antibody system. And then when he was very young, I think about 40 years, and the rest of his life, for 30 years, he worked on the issue of consciousness. And he developed this DNGS model where he said that in our head, a set of neurons, he calls it the dynamic core, which is a small set of all the neurons, but in numbers still a very big set because we have billions of neurons in our head, that interact very intensively, form consciousness in our mind. That means these active neurons in the dynamic core are the neural correlate of consciousness. And there's a lot of interactions between them, forth and back, feedback loops, feed-forward loops, and so on. And these lead to emergent properties. And emergent consciousness is thus an emergent property which supervenes over the activity of the interacting neurons in the dynamic core. And what they also posited in their DNGS model is that the dynamic core interacts with the other areas of the brain by input port and output ports. That's a very nice way of looking at it. So when you, for example, give a command to your larynx to produce speech, you just give them a word, and there's some autonomous process that controls the muscles of the larynx to give the sound to the environment. And the same on the input port. When you see from the 2 eyes a picture of a car on the road, you don't get pixels, but you get into the dynamic core already a car on the road. This is all pre-processed in subconscious processes of the human brain. So there's a lot of the processing in the human brain is not part of consciousness, but is part of unconscious processes. This is very important when we talk about autonomous driving and so on later on, because there are many unconscious processes, and the fantastic capability of the human mind is there's this borderline between conscious and unconscious can be moved by training and experience. If you, example, start a sport, originally the commands are conscious when you start skiing or riding a bicycle or playing a musical instrument. And if you do enough practice, it moves to the unconscious and you can give a higher level command and the whole thing will unfold. That means we can change the physical structure of the brain by training and by learning. And that's, I think, an important issue. So generally, when we fall asleep, our consciousness disappears, but many unconscious processes will operate in parallel as if nothing has changed because they are needed to keep us alive. Okay? So now, having introduced this model of the human mind, the question is, what is now the essence of communication among humans? The essence of the communication is a basic natural language sentence, and you will see later on that this structure we find in many different areas of computer science. It's a subject, a predicate, and an object. And the subject can be a person, a thing, or a construct. A predicate will be a relation. And what is important in natural language, that the relation is very often tensed. In German, we call the predicate a Zeitwort. It means a word that expresses time. And then we have an object, which is a refinement of the relation given in the predicate. And the sentence only makes sense when all three parts of the sentence are grounded, are meaningful. If one of the parts is not grounded, the sentence doesn't make sense. It doesn't carry information. So the idea carried by the sentence is called an information item, or we call it an item as it is abbreviated up here. It's a core new term in the DRT model. So we're now in a position to give a picture of the human communication according to the DRT model. We have some item in the mind of the sender, which is in the dynamic core of the sender. We encode it into words, and this is done in the language memory, more or less by autonomous neural circuitry. You don't, when you speak, you don't realize how your ideas are transformed into words. If you speak a native language, if you speak a foreign language, this process is normally controlled by your consciousness, and then you don't speak fluently in a sense. So we now have to view two goods, either by speaking, then we give control commands to our larynx. We generate streams of sounds. They are picked up by the ear of the receiver, decoded into words in the autonomous language memory, and then finally the item is recovered in the mind of the receiver. Give you an example. Let's say Tom possesses a valid password. Now this sentence is semantically meaningful. There's nothing wrong with it. But is it denotationally meaningful? Well, this depends. Is the time of utterance, the point when I speak this sentence, is this within the time interval contained in the passport? Because a passport is only valid from to. And if the statement, since this is in the present tense, if the statement is spoken at the time which is within the interval of the validity interval in the passport, then this sentence is true. If the sentence is spoken outside this interval, then this semantically meaningful sentence is false, because it doesn't have a valid passport at that time. The question now is, if we write this sentence on a piece of paper and the reader reads it at some later time, It depends on the time of reading if the sentence is true or false. Because when he reads the sentence at the point of reading, which is outside the validity interval on the passport, then the sentence is false. So what is very important in human, in audio communication, is the point of utterance of the sentence. So when I look at the written text, we have the write event and the reading event, and we can, the interval between the writing event and reading event tells me when the proposition is true or false. Now, it's not always as evident as it is in the passport, but in generally speaking, if I say a sentence, I always have some implicit understanding of the time the sentence refers to. Excuse me for a moment. Let me now go to the other part of information, which is also very important, and that is the emerging information flow. May I ask you, who knows about the emerging information flow? Anyone ran into this? I think this is a very important concept, and it's a different way of bringing information from a sender to a receiver without using symbols. And that's the way I change the environment by my actors, and the environment is looked at by the receiver, and so this is an indirect transfer of information from a sender to the receiver by the changing in the environment. And a very good example of Stigmatic information flow is the traffic light. The traffic light is changed, and the whole traffic. I mean, I communicate with other cars without even speaking the same language, and see what they do and they reason what they want to do because of their actions and act accordingly. So there's a lot of information. Now, why is this so important? In many real-time systems, the Stigmatic information flow, that means the changes of the environment, and then the perception of the changes by some other system, part or whatever, causes a closing of a link in a loop. That means by the Stigmatic information flow, a loop is closed between the sender and receiver. And whenever we have a loop, we have the possibility of emergent behavior. And emergent behavior is something which we sometimes want, but many often we don't want emergent behavior, because if you put systems together, all of a sudden the system has different properties than the subsystems. And this is caused by emergent behavior. And the cause for this emergent behavior can be the Stigmatic information flow. And this is in many cases overlooked by computer engineers. Now let us now go into more detail. I have to hurry up a little bit on the impact of time. I think the time is expressed by the predicate of the proposition, which is normally tensed. In the DAT model, we don't tense the time. We assume that with every predicate, we have an interval defined where the happening is valid. Okay? We use our notion of a global time. And then over time, the context changes because, as I said, the word changes and our conceptual landscape changes. And during the interval between the write event and the reading event, the context can be altered. And as I have shown you on the passport, the information can lose its validity. Coming to. Now, in oral communication, this is of less concern because the 0 point of the address is the same for the sender and the receiver, that is the speaker and the listener, and they don't have this delay, which is part of the written communication. Now, how do we handle time in the DAT model? When we handle time, that we give temporal parameters to the predicate. That means if it's an event, 1 timestamp, if it's a state, 2 timestamps, and it is assumed that all involved parties have access to a global time, to GBS time, and agree on the global time and can interpret the timestamp because of their knowledge of the global time. Now let me go to another important for computer systems to the tokens. The tokens, as said, are meaningless placeholders, the token names that hold the token. And consider the statement A times B is C. And I give the tokens values, then there is 3 times 5 is 15. Now, what does it mean in reality? I don't know. Only after I have given meaningful names to the variables, this becomes a meaningful statement in reality. Or, on the other side, if you consistently change the names of all tokens in the program, the meaning of the program doesn't change. That means the tokens have no relation to reality. Token names and values by themselves are not grounded, and this is a really important insight. Let me give you an example about tokens in cyberspace. Let's assume I have 3 dishes on the table with 5 apples in there. And if I say A is the number of dishes and B is the number of apples on the table, then C is the number of apples on the, if B is the number of apples on the dish, then C is the number of apples on the table. Then I've grounded the words. And then this becomes a meaningful statement. As long as I only use A times D times C, the statement does not have meaning in the sense I defined it before. So, in a sense, a grounded variable is a degenerate item. And the question of how to ground variables is very important when you talk about the correctness of algorithm. An algorithm implemented in the program implements a relation among meaningless tokens. And if these relations, if the names of these tokens are grounded, then these relations in the abstract token system world become actual relations in the real world, because then the token names refer to real concepts in the real world. And then I say a program is accurate if these actual relations are correct in the real world. So the correctness of a program depends actually on the meaning of the variables. This is the definition. A good consistency of a program, I could say, if I multiply it correctly, but that's not the issue here. It's how the program relates to reality. Now let's summarize here the difference between words and tokens. A word is a signifier, it's the same, a token is a variable name. The signified on the word is the concept in the human mind. On the token, it's a value denoted in the placeholder. And the meaning, which is not grounded, this is why I call it content here, is the use of the variable name in the program denotes the relation among the variable names, but doesn't tell you what is actually happening in the real world. So let us now go to the characteristics of a data item. In the DIT model, a data item is a symbol that consists of a signifier and a signified. And the signifier is the name of the symbol. And if we use human communication, the signified is a concept. If we use a computer system, the signified is a meaningless token name. And only if I ground the token name, then the whole thing gets grounded and has meaning in the real world. But in both cases, a data item is a whole that consists of 2 parts, a signifier and the signified. And if you look at the characteristic of an information item, I say our item informs us when the predicate holds. It doesn't say whether the proposition is true or false, because this depends on other things. There can be fake news or it's also kind of information, false information. So we don't assume that our concept of an item, of a proposition is true. The relativity, an idea somehow is abstract, but the presentation of the idea requires a certain context. And the context is always relative to some surroundings, a language context or whatever. So we cannot have any absolute representation of an item. An item is always dependent on the current physical and cultural environment. And the aspect of newness of information, which is also part of some theories of information, is not part of the DAT model, because we don't know what is the information content in the conceptual landscape, and I don't think we can ever know it, so that we can say if this proposition is new to the receiver or not new to the receiver. Now, we'll go very quickly over some other things. If we go to an archival information, an archive is a repository that holds documents of permanent historical utility, of past information, and many different items. And as I said, an item consists of a value and an explanation of a value. And in an archival system, the value is the data element in the database, and the explanation is given by the schema of the database. The structure of the database gives me the value. So let me give you a simple file system as a schema. Then I have a file name, a column name, a row name, and a value. And the value is explained by the row name, the column name, and the file name. And of course, I can use different representations. What is often missing is the temporal information which is needed in the DAT model. For example, if I take this example of a simple file, the number of students, I say Paul and N, the size and weight, and then I can measure it on, have the temporal information, and then the entities, Paul and N, the properties, size and weight, and the values. And that's, but I can store this in a completely different form, for example, in the knowledge graph, and then an item becomes a primitive element of a knowledge graph. And I don't know if you looked at knowledge graph, basically the primitive elements are items, but I need the temporal information on the link between two entities. And I can store it differently. I can say I give a file for every student, and then I get a different data structure with the same information. So this is nothing fixed. And when I call it database, it's this summary of all the files that I'm interested in or containing in the database. And how it is structured is, of course, important for accessing, but not for the conceptual thing. So what is, when I go to real-time system, then the items have a limited temporal validity, because I can only use an information in a control system if it's still temporally valid. The question now is that this temporal validity becomes a very important point to determine between useful and wrong information. And so we have normally a deadline until we have to put an action. For example, if you talk about engine control, I have to precisely inject the fuel into the engine at a particular point in time, which is down to about microseconds in the time range. And I must make sure that they keep the deadline. And so I must guarantee that my algorithm doesn't take longer. And in this sense, we talked about deadlines. I think anytime algorithms are extremely important in real-time systems that give you satisfying results early and then improve the results as the algorithm continues operating. Well, let me go a little bit. But I am skipping this data biological system because we are already short on time. But let me summarize in this first part of the lecture, the most important, that humans process items and machines process data. And that's the fundamental difference between, or a fundamental difference between human information processing and machine data processing. Now, what you can learn from this? First, the classification dilemma. I mean, whenever I use natural language, there are the possibility of different interpretation of the words, because we have a subjective conceptual landscape, we have our subjective meaning of the words, the connotation of the words, and the use of these different meanings in language can give rise to a lot of problems in specification. Now, if a computer interacts with another, the problem does not exist. They can use formal specification and don't have this problem. But whenever the human comes into this specification problem, pops up, and it comes up particularly, what is the purpose of a system? How do I ground the symbols? How do I make these interfaces between cyber world and the physical world? And sensors, actuators, and of course the human-machine interfaces. The next one is in the human-machine interface design. I must very well look at the conceptual landscape of the user to define the right representation of the items at the man-machine interface, at the human-machine interface. Because the mind of the user is the receptor, so to speak, of the information. And if I don't have a clear, if I'm not clear about what a user associates with a word, it can give rise to misunderstandings. And I think the global time, which is part of the DFT model, is, I think, a very important parameter, I could say, a very important variable in any real-time system, particularly in a real-time system, if it's distributed, because it's needed to introduce the timestamp and to interpret the timestamps. I can design unidirectional communication channel with error detection, which separate the sender from the receiver. And the receiver has no impact on the sender. It's still a error correction. And I think this is probably the most important aspect of the time-triggered protocols. And I can install time-triggered communication channel which do not have any unforeseen delay between the sending and the receiving of an information. And I can give you an example how important this would be in the smart grid. Okay, I think I stop here because I think we're already at the end of the time. And to summarize, the DFT model makes a clear distinction between the terms data item and information item. A data item is a symbol that is meaningful if the signified is grounded, while an information item is a time proposition that is composed of a grounded data items and carries an idea that it makes sense. And again, humans deal with items while machine deals with tokens. Thank you very much.